So the last concept in this chapter is pi bonding. And pi bonding occurs when you have sideways overlap between two parallel orbitals. And these parallel orbitals are typically unhybridized. Usually p orbitals, but they can also be d's. We'll see a more obscure example at the bottom that involves d orbitals, but usually it's p's. And so to see how this is going to work, let's look at the molecule ethylene, which is C2H4. If we draw out the Lewis structure for C2H4, we will discover that there is a double bond between the two central carbons. This is a molecule that has two central carbon atoms. Each carbon atom has a steric number of 3, and so we will get two adjacent trigonal planar shapes in the same molecule. In order to make trigonal planar and have a steric number of 3, I have to put 3 orbitals into the blender, which means sp2 hybridization. So an s and 2 different p's are all going to mix together, and that forms these yellow orbitals here in the picture. So this is sp2, this is sp2, and this is sp2. Those orbitals are then able to form sigma bonds with hydrogen here and here, on the other side of the molecule with hydrogen here and here. And then these two can also overlap directly together. The two carbons are going to form a sigma bond in the middle there. So there are a total of 5 sigma bonds in this molecule. That leaves on each carbon, though, a p orbital that is unhybridized. And that unhybridized p orbital on each carbon is sticking straight up and straight down through the center of that trigonal planar arrangement. And notice that the carbon on the left and the carbon on the right, those unhybridized p orbitals are parallel to one another. And so this second bond here, we'll go ahead and change colors here. This second bond that I've drawn in green, this becomes a pi bond. And the pi bond occurs when those two p orbitals overlap side to side. So the overlap is here in between where those two orbitals would have normally been. Notice that there is a region of overlap above and below the sigma bond in the middle. So this is a sketch right here of a double bond with the pi above and below and the sigma in the center. If we look at acetylene, which is down here, it's what they use in welding torches. C2H2 is the fuel. Notice that there would be a triple bond between the two central carbons. Because the steric number on each carbon is only 2, we would have sp hybridization. We would get a linear geometry. So here's sp on this carbon in yellow, here's sp on this carbon in yellow. The sp on the far left overlaps with the hydrogen to form a sigma bond. The sp on the far right overlaps with that hydrogen to form a sigma bond. And then the two sps in the middle overlap with each other to form a sigma bond. That leaves 2 p orbitals on each carbon that are unhybridized. So what I'm showing in green here, going up and down in the y direction, if you want to think of it that way, on the paper, that will form a pi bond here. And you can only see part of the bottom of it because it's covered up. And then again, I'll switch colors. I'll use purple now. You also have p orbitals that are coming out of the paper toward you and behind and into the paper. Those orbitals can overlap side to side as well, and then there's another set that's behind that you can't really see as well there because it's hidden by the sigma in the middle. So you've got a sigma bond in the middle in yellow, you've got a pi bond in purple that's in front, and you've got a pi bond in green that's above and below. And so that's a triple bond. Now, it is possible to use d orbitals for this. Here is a picture of sulfuric acid. Remember that we put the hydrogens on the oxygens, not on the central atom, when we do an oxoacid. And in order to reduce the formal charges on that central sulfur, we are going to double bond the two oxygens that don't have hydrogens on them. In this case, those double bonds would be, because this is already sp3 hybridized to begin with. The sulfur has a steric number of 4. So we've used up all the S's and P's, so there aren't any P's to double bond with. So these pi bonds here would be using d orbitals. D orbitals from sulfur anyway. Oxygen doesn't have any d orbitals, so that's going to be a overlap between unhybridized d orbitals in sulfur and an unhybridized p orbital of oxygen. And this is shown actually on the next page. So this is sort of a sketch of what a pi bond might look like between a d orbital and a p orbital. So you've got overlap above and below. Again, your nucleus would be here in the center of each atom. So this would be like your sulfur and your oxygen. So the summary of this section is anytime you see a single bond in a molecule, single bond, that consists of a sigma bond. Anytime you see a double bond in a molecule, you know that that is made up of 1 sigma and 1 pi. And anytime you see a triple bond in a molecule, you know that you have 1 sigma and 2 pi bonds. So basically, you always have a sigma bond, and then if your bond order is higher, then you add on pi bonds until you get up to the bond order that you need. So if your bond order is 1, then 1 sigma is all you need. If your bond order is 2, then you need 1 sigma, 1 pi. Bond order is 3, 1 sigma, 2 pi. The last segment of this video then will go over the last couple problems here on the next page. You can take a stab at those. Number 11 is those same 6 molecules and ions that we've been working with, and then 12 and 13 have you getting in more to the sigma and pi bonding stuff.